How are you doing? It's Mike here, and in this video we're going to talk about solving radical equations. So if you are following this series, in the last video you would have seen how to solve rational equations, and I know many of times in your college algebra classes or algebra classes they like to group these two topics together. However, they still are slightly different. So we follow a similar idea that we're solving for something. However, solving radical equations and solving rational equations are slightly different. So before we go on to the idea of solving a radical equation, I'd like to review an exponent property, some of our exponent properties. So let's review a couple of our exponent properties. There we go. So the first one is if we are raising one exponent to another. So if we have x to the m raised to the nth value, where m and n are both rational values, we can identify a property by multiplying our exponents together. We would get x to the m times n values. So for example, if I have x squared to the fifth value, that's going to be x to the 2 times 5, which gives me a value of 10. That same property could be held true if I have x to the 1/2 and I raise that to the second value. That's going to be x to the 1/2 times 2, and 1/2 times 2 gives me x to the first. So it doesn't have to be necessarily an integer exponent value. We could have a rational value that is in the form of a fraction less than 1. So let me rewrite this so we can see this a little bit better. This is a value of 1/2. This is a value of 1/2. So let's think about what happens if I were to give you x to the 2/3. And I would raise that to the 6th power. This would be x to the 2/3 times 6. We recognize that 3 goes into 3 once, 3 goes into 6 twice. So this actually would be x to the 2 times 2 power, which is x to the 4th power. So just as a reminder, if you're raising one exponent to another, they call this the exponent power rule, then we would multiply our two exponents together. Let's just talk about a radical conversion. So let us talk about a radical conversion to exponent form. So this states that if you have the nth root of x to the mth power, this will give you x to the m divided by n, x to the m divided by n exponent. So let's go ahead and look at the most common example. Let us say that we looked at the square root of x. Let's say we want to convert this to an exponent form. So even though we don't see the index, whenever you don't see the index of a radical, we automatically know it to be a value of 2. Just like whenever we don't see the exponent of a value, we automatically know it to be a value of 1. So using our formula above, if we want to convert the square root of x to a exponent notation, we can write this as x to the 1/2 power. We can write this as x to the 1/2 power. Very similar, if I want to convert the third root of x, if I want to convert the third root of x to an exponential form, this would be, again, that's a value of 1 even though we don't see it. This would be x to the 1/3, x to the 1/3 value. And let's try something that has an exponent slightly different than 1. Let us try the 5th root of x to the 4th power. This would be equal to x to the 4th power divided by 5, because we are following the same exact protocol. We are following the same exact protocol. That's a 4. Of that formula. So that would be x to the 4/5. So I always like to think about operations that counteract each other. So sort of like yin and yang. If I think of a positive, I think the opposite of positive would be to subtract. Just like if I see a divide, the opposite of division would be to, if I just see a multiplication, the opposite of multiplication would be to divide. So if I see a square root, I think the opposite of my square root is to square. And let's talk about why that is. If I were to give you the square root of x, and if I were to square this, this is really going to be converting the square root of x to exponential notation, x to the 1/2 squared. And when I square 1/2, I'm going to multiply their exponents because I have to obey the power rule. So I get x to the 1/2 times, that's 1/2 times, let me write that a little bit bigger so we can see it, 1/2 times 2, which gives me 1/2 times 2 is a value of 1. So the opposite of the square root is to square. So let's say I ask you to determine what is the opposite of the third root. What is the opposite of the third root? So let us think about this. Opposite of the third root, if I want to convert this to a rational exponent, I would say this is x to the 1/3 exponent. And what value would I have to raise 1/3 to that gives me a value of 1? And that, ladies and gentlemen, is going to be a value of 3. That's going to be a value of 3 because we know 1/3 times 3 gives me a value of 1. So that's just a value of 1. So the opposite of the third root is to cube. The opposite of the fourth root is raised to the fourth power. The opposite of the fifth root is raised to the fifth power, and so on. So that follows a trend. And now since we understand our rational exponents, let's go ahead and try a problem. So let us go ahead and look at an example and say we want to identify and determine, and the question will say to solve, where does the square root of 3x minus 4 equal to 1? And the instructions for these will state to solve. So the part that's similar about our last couple videos is that we have to identify a domain. Or when I say we have to, we could identify a domain of this problem, because whenever we have radicals, for example, a radical that has an even index, like 2 is an even index, 4 is an even index, 6 is an even index, we have a domain issue because we know the radicand must always be greater than or equal to 0. Greater than or equal to 0. So we could add 4 on this side, and we get 3x must be greater than or equal to positive 4, and divide both sides by 3, and we get x must be equal to greater than or equal to 4/3. So this is going to be the domain of this problem. Therefore, if we get a value that is less than 4/3, then we know we have to exclude it because that would violate the constraints of the domain of the problem. However, I will tell you that sometimes, especially if we have multiple radicals, you have to figure out where our domains overlap, and then you have to determine if the solution violates one of those constraints. Sometimes identifying the domain of the problem and then comparing it to your final answer in this circumstance could be more time-consuming than it's actually worth. So in these problems, I always recommend always plug in your solution. Always plug in your solution because it is much easier to see if it works by plugging in, and most of the times it's going to be quicker. So let's think about this. If I want to eliminate that square root, what is the opposite of the square root? And the opposite of that square root is to, in fact, square. So if I square one side, I am also going to have to square the other. So the opposite of the square is to take the square, or the opposite of the square root is to square. So on our left side, the square root and the square cancel out, and we're left with our radicand, which is 3x minus 4. And that is going to be equal to a value of 1 squared, which is just a value of 1. So now, by us squaring the left side and squaring the right side, we've eliminated that square root. And now we're going to go ahead and add 4 on both sides. So we get 3x is equal to positive 5, and divide both sides by 3, and we get x equals to a value of 5/3. Okay, awesome. But now we have to check to make sure this does not violate the constraints of our domain. So if we think about this, okay, so if we have x being greater than or equal to 4/3, that's our rule. X must be greater than or equal to 4/3, and we have x equal to 5/3. 5/3 is obviously 4/3 plus 1 more third, which gives me a value of 5/3. So this is definitely greater than, so it does not violate that constraint. But however, sometimes that's not as easy as for us to see. So I always recommend plugging in. So let's go ahead and plug in and see what happens. So we're going to have the square root of 3 times our solution, which is we determined to be 5/3. And then we're going to subtract off 4. This gives us the square root of the 3 and the denominator 3 cancel, so we get 5 minus 4, and that equals to the square root of 1, and the square root of 1 equals to 1, and that's what we expected our solution to yield at the beginning. So by us plugging in, sometimes that's a little bit easier than determining the domain of the problem and then comparing that to our final solution.